Okay, we've got one more wave property to talk about, and then we're going to go over some calculations we can do related to energy with waves. So it's important to note that so far when I've talked about waves, I've usually talked about traveling waves, the idea that waves move, but that's not true for all waves. Standing waves, which we can also call stationary waves, remain constrained within some region of space, so they're not actually going to change in location. This is important specifically for our understanding of electronic structure of atoms and molecules. We can talk about electrons as standing waves. So it turns out when we start talking about subatomic particles, electrons are small enough that we can actually see wave-like properties with them, in addition to thinking of them as particles. So the concept of a standing wave is important for understanding an electron. So an example that is easier to interpret that has some physical reality you can deal with is if you had a vibrating string and it's held at two ends points, that's an example of a one-dimensional standing wave. So let me get this ready. So here's an example here. You'll notice that our string, if we want to make a standing wave and we have two endpoints, that to do that, you can't just have any wave show up in here and have it be a standing wave. You need to have it so that at these nodes at the end, it goes to 0. So for example, in this top example here, you have one crest, and then on the other side, it would have one trough, right? And then you'll notice as you go down, you have 2, 3, and 4. You can't fit 1.5 crests inside a standing wave because then it would change its position. It's going to change the structure, but it won't be a constant where it is the same place all the time whenever it's in that area. So the points of our string act as our endpoints that we're able to get, and then the standing wave doesn't look like it's changing there at all because of that. So it has to somehow evenly divide. There have to be an integer number of nodes between those 2 points. So, and because by integer number of nodes, I mean like the top one there's 0 nodes, the second one there's 1 node, this third one there's 2 nodes, and the fourth one there's 3 nodes here. So we have to have some integer number of nodes, well, a whole number, it can't be a negative, so somewhere between 0 and infinity, so to be able to make this work. Now we mention this just because it's going to come up as we think about electrons. We can think of them as standing waves is our interpretation sometimes, depending on what structure you're using to talk about an electron, because we'll use different properties depending on what we're interested in, and you can understand them a bit differently in different contexts. Now, we've gotten through that. So that's the last of our terms related to that. So now we're going to go to energy. So a light wave, so we're talking about light here, remember it's because light is going to interact with our atoms, and that's how we're learning about them. So that's why we're so concerned with light in this chapter. So light has wave-like properties, but Einstein discovered that some of the properties could only be understood by describing light as coming in packets of energy called photons. So even though light is a wave, it also has some other properties that are going to limit it. Like when I think of a wave, I don't think of it the same way I would think of as a discrete packet of energy. And what I mean by that is that a wave could have any particular size, right? So it could have different amounts of energy, and it would be fine for it to go incrementally up no matter what. What we found through experimentation, though, as scientists, was that it could only take certain values, and that this means that we could think of our light and we could shrink it down to this is the smallest amount of light you can have of a particular wavelength, and we call that a photon. So there's a limiting factor. I can't have infinitely small light is the idea. So light comes in quantized sections, which means that it comes in certain amounts of energy. So there's a minimum energy for a particular wavelength, and then I can have twice that energy, 3 times that energy, 4 times that energy, which corresponds to thinking of it like photons here. So our photons, we can have like 1 photon, 2 photon, 3 photons, 4 photons, a mole of photons, if you keep going up, but you're not going to have 1.6 photons is the idea behind that. And so we have an equation we can use for this. So the amount of energy that exactly 1 photon of light carries is directly proportional to the frequency of the light. So energy equals h nu. Remember, nu is our variable we use for frequency. It's going to be in 1/seconds, which we can also write as hertz. H is a constant known as Planck's constant. Anytime in this class we use, you'll get a copy of this. It'll be on your exam. You don't have to memorize it, although if you do, it's helpful. You'll use it a lot. This constant shows up a lot when we talk about things like electrons and light photons, things that are very tiny. There's some different quantum effects, and this constant is related to a relationship that's there. Planck's constant, we're going to use 6.626 times 10 to the -34th joules per second. What we also know If energy is related to the frequency, it could also be related to the wavelength. Because remember in a previous part of the chapter, we looked at the idea that the speed of light is connected to both the wavelength and the frequency. So if I know one, I know the other. So we also have an equation related to wavelength, and the energy of a photon is inversely proportional to that. Sorry, this here, I will fix on my version. This should say inversely proportional to wavelength, not frequency. That was my bad. So E equals hc over wavelength, which we also write as hc over lambda. Note, you need to make sure that your units work out for this. To make this turn into the correct units, your speed of light and wavelength need to be in the same units of length. So if your wavelength was given to you in nanometers and you're using the speed of light in meters, you need to convert your wavelength into meters. You could also convert the speed of light to nanometers. As long as they match and they cancel out, it's fine. And then the seconds part of the speed of light will cancel with the seconds part of of the Planck's constant, and you'll be left with joules, which is our measurement for energy. So what this means in terms of the fact that there are individual photons that we're working with, this means that while light is going to have some wave-like properties, it also means it can be understood as being transferred closer to something you'd think of like a particle. When it's being transferred in packets, we call photons. And so photons are going to represent the smallest amount of light that can travel. We won't have half a photon of light. So now let's take a look at this. We can do calculations like this one, right? So what is the wavelength of a photon that has an energy of 6.52 times 10 to the negative 19th joules? So we set it up. We know that energy equals hc over wavelength. And so we have to rearrange this equation to solve for wavelength. So I'll get that wavelength equals Planck's constant times the speed of light over energy. I multiplied both sides by wavelength first, and then I divided both sides by energy to get wavelength by itself. And that's what gave me this arrangement. So if we plug these values in, we get 6.626 times 10 to the negative 34th joules seconds. Our speed of light, we're going to use 3.00 times 10 to the 8th meters per second. And then our energy was given to us in the problem of 6.52 times 10 to the negative 19th joules. So you can see the joules would cancel, the seconds would cancel, and we'd be left with meters, which makes sense for a wavelength. So now I've just got to plug all these in. I grab my calculator. So we put all the stuff from the numerator in first, multiply it together, divide by the stuff in the denominator. And when I do that, it would help if I put the right numbers in my calculator. So yes, if you do not put in the numbers that you're actually calculating with, you will get a wrong answer. So this will tell me that the wavelength would be, and I'm going to have three significant figures because that's what I have in my energy. It'll be 3.05 times 10 to the negative 7th meters. For this problem, note this would be a sufficient answer. I also want to point out you could convert the units to something else. Let's say the problem instead asked for it in nanometers. Let's look what that would be. So if it had asked you for a specific unit, or you're working with like a multiple choice question, all the answers were in, let's say, nanometers, then we could convert it. So as a reminder, in 1 meter, there are 10 to the 9th nanometers. It's also true that 10 to the negative 9th meters is equal to 1 nanometer. Both conversions work. Use whichever you're more comfortable with. So I like saying how many of the small one fit into the big one. So that's how I tend to write my units. So here, our meters would cancel. When we multiply this out, we're going to get 305 nanometers. Note that both of these are perfectly fine answers, this and the meters answer. You would just depend on if there's some reason for context that you need one or the other unit. Just make sure to pay attention to that. Don't ignore the fact this number has a unit. Okay. So here's a second question. What is the frequency of a photon that has an energy of 2.43 times 10 to the negative 16th joules of energy? I suggest you pause this if you're watching, try to solve this yourself, and then watch me do it. Okay, hopefully you paused for that. So we have energy equals h nu, and then I'm solving for frequency, so I'm going to divide both sides by h. So I get energy divided by Planck's constant equals the frequency. So now we plug our values in. We're given an energy in the problem, 2.43 times 10 to the negative 16th joules. Planck's constant is a constant, 6.626 times 10 to the negative 34th joules seconds. The joules would cancel. And I'll plug these in. Negative 16, 6.626. And when I do that, I'm going to get 3.67 times 10 to the 17th, and this is 1 over seconds, which you can also write as hertz. And note, you can also get s negative 1, 1 over s. These are all the same unit. Now, something to note about problems we're doing in light compared to some other sections of chemistry is you will get very varied answers in terms of what types of powers for your scientific notation make sense. So frequencies for some of these wavelengths of light can be very large, like this number here, 3.67 times 10 to the 17th, and that's okay. And that's something you have to be comfortable with in this chapter, is there's going to be a lot more variation in what you get for both wavelengths and for your frequencies than you might be used to from other sections, where there are a lot of chapters where honestly the reasonable answers are between like 0.001 and 1,000. And if you get something like 100 trillion or something, 10 times 10 to the 18th, there are a lot of questions where you're like, that doesn't make any sense. I probably didn't weigh 10 to the 18th grams on my scale. But in this section, you're going to have a lot of numbers where you have a lot more variation. If you know more about the light you're working with, for example, if you know it's visible light versus infrared versus an X-ray, over time you can develop intuition for, okay, visible light will be around this. For example, its wavelength is going to be in some number that is in hundreds of nanometers probably, or 10 to the negative 7th meters, if it's visible light. You can get the same feel for frequencies and energies over time, but for right now, especially if you're not given a specific type of light, you won't have that context, and that's okay. So don't freak out if your number is really, really large or really, really tiny in these problems. Okay. So now, why are we so concerned about light, and how does it relate to our atom? So when an atom or molecule absorbs energy, the energy has to go somewhere. The energy doesn't just disappear into nothingness. So what happens is a lot of times this energy is related to an electron changing what energy level it's in inside of an atom. And we'll talk more about electron energy levels in the next section, or maybe later in this chapter even, next chapter. But either way, what's important is the atom, the electron, can absorb energy. The wavelength of light that any atom or molecule can absorb will be unique in the sense that it makes it like a fingerprint for that particular substance. So remember, wavelength is directly connected to energy. So the amount of energy that it takes for an electron to move between particular energy levels is going to have a particular wavelength associated with it. So two examples shown here are a spectrum in the visible spectrum for what it looks like for hydrogen to absorb light, and it has 4 distinct areas that relate to 4 specific transitions. And then second, it has iron, which has a whole bunch of transitions. You'll notice some sections are just so thick because there are so many next to each other that do that they look like just a big bar, but they're actually a bunch of tiny individual ones that if you were able to look at this measurement very carefully, there would be some distinction in between, and you could get the exact wavelengths of each of those. And each of these lines represents a different electron transition that can happen. So that's why we're worried about light in chemistry class. There are other reasons too, but this is a big one, is that atoms or molecules are able to absorb light, and we can get information from how much energy it takes that the atom can absorb, and that gives us some knowledge about the atom. So what does that teach us, and why is that related to that? So we're going to start with the Bohr model of the atom. Note, this model is not perfect. There are some issues with it, but it still makes some good predictions that help us understand some ideas. It's not a perfect model. It's not the current one we use, but it's a good one as a starting point to explain why these transitions are particular energies. So what happens is Bohr's big idea that we care about is the energy of the atom is quantized. And what this means is that an atom can only release or absorb very specific amounts of energy. You can't just absorb any amount when you interact with it. That's why in the previous slide you saw lines at specific wavelengths. Each of those corresponds to an electron moving from one quantized energy level to the other. In Bohr's model, this is the part that's not quite right now, but it'll work well enough for us to understand this idea, the electrons travel in orbits that are a fixed distance from the nucleus. So the energy of those electrons will be proportional to the distance the orbit is away from the nucleus. Since as it gets further away, it's going to feel a less strong pull. Remember, these electrons are negative, and the nucleus has got a bunch of protons that are positive in it. So if you change the distance between them, you change that electrostatic attraction. So When electrons leave an orbit to travel to a new one, they can emit radiation if they go from high energy to low energy, or if you want to move them to one further away, you input the right amount of energy from a photon that the electron can absorb, or the atom can absorb, and specifically the electron moves its location based on that. And the jump in energy that occurs when the electron transitions up should be the same as the energy of that photon. That's why this is so specific about what wavelengths you see, since a particular wavelength can only provide a particular amount of energy. So the idea is we can look at this model where our electron is going to end up in different energy levels. And the examples here, given for the model you just looked at, which was those 4 lines, they correspond to these 4 wavelengths, or these 4 particular distances. So in a hydrogen atom, when the electron goes from something called n equals 6 to n equals 2, these represent different orbits, it's going to release violet light. Whereas when it goes from 5 to 2, it's going to release this blue violet light at 434 nanometers. So it's going to be specific wavelengths get released. I will note that this model is much easier to talk about for hydrogen. Once you get into multiple electrons existing at the same time, those electrons also interact with each other, and it gets more complicated. So we will stick to doing discrete calculations of just one electron, because actually you're not going to be able to do that with, you get more than one, but there's some ideas we can get some information about it, but that we stick that in our quantum mechanics course. So if you would like to learn about multi-electron atoms, come hang out with us some more, or you can go join physics people, they do that stuff too. So now, how does this happen and how do we learn about it? So when an electron absorbs energy, it becomes excited. So the electron transitions from that low level to a high level. However, it's not going to stay excited. It's instead going to relax back down and transition from a higher energy level to a lower one. When that happens, a photon of light is likely to be released. I say likely, there are other ways for electrons to lose energy through vibrations and other things, but in many instances they're going to release a photon of light. And if they don't, something else has to happen to account for the energy change. Since light of different energy values are going to have different wavelengths, we can use the color of light, or if it's not visible light, if it's something like infrared, we can use or UV. We can use the particular wavelength or frequency to determine the difference between those energy levels. And so this can be done with non-visible light as long as we use a detector that can detect it. Because that's the important part. You have to be able to know the light's coming off to be able to make this calculation. So the drawing from your text, the idea is electron starts down here at this lowest energy level and then jumps up to some other energy level, and these different arrows go to different points and are going to represent different wavelengths of light that it would need to absorb to be able to get to that energy level. Then once it's in one of these, it's going to jump back down. So for example, let's say we're in 5, it could go back down to n equals 2 first. It could then do a second jump like this from n equals 2 to n equals 1. So one photon could be absorbed to go from 1 to 5, and then we could see one transition from 5 to 2 and another from 2 to 1. So in the end, we're going to expect the atom to get back down to what's called the ground state. That's where it is in its lowest energy level and where the electron is as low as it could possibly be, but it doesn't have to transition back down all at once. You will sometimes see a transition where it happens more than one time. So that can explain why you see different wavelengths of light. Maybe it comes down different ways, and this obviously gets a lot more complicated if you have more than one electron in your system. Now, we can actually do a calculation with that with something called the Rydberg formula. So it turns out that if we take 1 divided by the wavelength, it's equal to r, which is a constant called Rydberg's constant, and then we have 1 over the final energy level minus 1 over the initial energy level squared. Note that this constant is specific to the atom hydrogen right now, and that's what we're doing calculations for because this can be done explicitly here. Since wavelength and energy are interconnected, you also have an equation for energy. So we have 1 over n1 minus 1 over n2 squared, and then k is the constant we have for that. Note, if you found the wavelength or energy, you could also use your equation to go between them. So once you know the wavelength, you can use E equals hc over wavelength, and that would work as well. So, okay. Determine the wavelength of light emitted from an electron, and a hydrogen atom makes a transition from n equals 5 to n equals 3. So we have 1 over wavelength, and I'll be honest, I don't remember Rydberg's constant, so I have to grab that from the other slide. 1.097 times 10 to the negative second inverse nanometers. Note, depending on where you look for this constant, you might see it in meters instead. Pay attention to units. This problem will go ahead and give us an answer that is in nanometers, but that doesn't guarantee if you used a different version of the constant, it might be in meters. So make sure to pay attention to that. And let me grab the other part. So we have 1 over the final, which is going to be 3, because this is our NF, where it ended up. So we have 3 squared minus 1 over 5 squared. So let me make sure there's nothing else to that equation. Nope, that was it. So now we just have a few things to put in. So we've got, basically we've got 1/9 minus 1/25, which is what you get from those two fractions. And then we multiply it by 1.097 times 10 to the negative second. And we're going to get here that 1 over wavelength, note we're not done yet, we don't have wavelength by itself yet, is 7.80, and then I'll say 801 times 10 to the negative fourth inverse nanometers. Note that in this problem, you don't have any measurements that are anything other than exact. N equals 5 and N equals 3 are exact numbers. So I'm not too stressed about significant figures. Just don't round your number to like 8 times 10 to the negative fourth or something like that. So now we need to get wavelength by itself. There are 2 ways to do this. One is you can multiply both sides by wavelength and then divide by 7.801 times 10 to the negative fourth nanometers, and that'll give you the value for wavelength. We can also invert both sides. That's where we raise it to the -1 power. So inverting, as long as we do it to both sides, flips both of these. So we end up with wavelength, and then we invert this number, just 1 over it, and we will get 1,282, and now it is nanometers since we inverted it. That's 1 over nanometers. You take the fraction, you flip it over. And so this would be my wavelength. That'd also be okay if you told me this was 1,280 nanometers. That'd have been fine as well. But yeah, so this is the wavelength for an N equals 5 to N equals 3 transition. And so this is an example of how you can use those equations to be able to solve problems like this. Okay, it's a good stopping point for this section.